Okay, so let's start our class. Okay, so for today we will discuss a new topic, and it is also our last topic. Okay, before before our final assessment. Okay, so this topic will also be asked in your final assessment. Okay, so it is called infinite series. Okay, so firstly we have to learn what is sequence, okay, before we go to the series. Okay, for definitions of the sequence, it is an infinite sequence, or simply a sequence, is an unending successions of numbers, and the numbers are called terms. Okay, so like a1, a2, a3, a4, and so on. It's like this one: 1, 2, 3, 4, 5, and so on. It is the sequence of positive integer. Okay, and there's 1, 2, 4, 6, 8, and so on. Okay, it is infinite sequence. Okay, up to plus infinity for even integer. And this one also is a sequence. Okay, 1, -1, 1, and -1 again, and so on. Okay. If we are given the sequence or the numbers which form the sequence, we can actually form the general terms of the sequence. Okay, as for the example, here we have 1/2, 2/3, 3/4, 4/5, and so on. Okay, so from this sequence, we note that the denominator is larger than the numerator by 1. So 1/2, and this is 2/3. So 3 is bigger than 2 by 1, 4 is bigger than 3 by 1, and so on. So the general term is given by n divided by n plus 1. So this is the general terms. Okay, so this is the sequence. Okay, the second one is 1/2, 1/4, 1/8, 1/16, and so on. So from here, we know that the sequence is 1/2 to the power of n. So when n is equal to 1, it is 1/2. When n is equal to 2, it will be 1/4. When n is equal to 3, it is 1/8, and so on. Okay. So anything, any sequence, we can actually find the general terms. Okay, like this one, we have like alternate sign, plus and minus. So one is plus, another one is negative. The next one is plus, and another one will be negative again. Okay, so this is 1/2, this is 2/3, this is 3/4, and this is 4/5. If you look at the sequence, it looks similar to A, but the difference is only the alternate sign. Okay, so the if we try to connect with the first one with A, it will be like this: n divided by n plus 1. But we have to include the negative sign. So for the negative sign, it will be -1 to the power of n plus 1. It is not to the power of n because if it is n, this will be -1 to the power of 1 for the first one. So the first one will be negative. It should be -1 to the power of n plus 1 because the second one will be negative. Okay. If you consider just to the power of n, then the first one must be negative. -1 to the power of 1 will be negative for the first one. Okay. Okay. I hope everyone understand that. Okay. Next. A sequence is a function whose domain is a set of integer. So this is the definition of the sequence. So it means that we can map the sequence with the domain of the set of integers. So like this one, this is the sequence 2, 4, 6, 8, and so on. Okay. So the general term will be 2 multiplied with n. Okay. And then the domain of the integers will be 1, 2, 3, 4, and so on. So 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6. But what will be the function that connects all the mapping? It is f of n equal to 2 multiplied with n. Okay. And then we have a graph of sequence. Okay, so let's say you have y equal to 1 over x. 1 over x, x is greater than or equal to 1. So you have the graph y-axis, and this is x-axis. X is greater than or equal to 1. So it means that the graph will start from x greater than or equal to 1. Okay, and then we have 1 over x. Okay, when x is equal to 1, it will be 1. When x is equal to 2, it will be 1/2. When x is equal to 3, it will be 1/3. When x is equal to 4, it will be 1 over 4. And as x tends to almost infinity, x tends to infinity, then the y will be almost 0, but it will be never 0. So this is how we draw the graph of the sequence for 1 over x. Okay, next, the limits of the sequence. Okay, next is the limits of the sequence. So let's say you have this sequence here, n plus 1. Okay, so the limit of the sequence for this will be what? It will be increased up to infinity. If you substitute infinity for n here, this y will be infinity. So that's why the term of the sequence n plus 1, okay, increase without bound, because it goes to plus infinity. Okay. It's the same for other graph. Okay, you can see that, let's say for this one, as n tends to infinity, negative 1/2 to the power of infinity. Okay, it will be what? Negative 1/2 to the power of infinity. Negative 1/2 to the power of something big will give you, I think, will give you almost 0, right? Okay, can you check with the calculator what happened if you set negative 1/2 to the power of, let's say, 10,000? What will be the numbers? Is it goes to a very big number, or is it goes to 0? I believe it should be goes to 0. Okay, can you please check now?
0.
Okay, so it should goes to 0. Okay, so that's why for the term 1 will be the limit values. So 1 plus 0 will give you 0. Sorry, 1 for the limiting values. Okay, so it is for the fourth case. Okay. Okay. Okay, next we have definition. A sequence AN is said to converge to the limit L if given any epsilon greater than 0 does exist a positive integer n. So this is just by definition. If you learn more complicated mathematics subject like real analysis, then you have to go through all this definition. But whatever it is, for this class, you only have to know that a sequence an is said to converge to the limit L if you have limit an tends to plus infinity is equal to L. So let's look at the example here. The first two sequence in figure 9.1.2 diverge, and the second two converge to 1. Okay, so it says that the first one, is it this one? 1.1. Okay, this one. It says that the first two diverge, but then the second two converge. Okay. And then limit n over n plus 1 as n tends to plus infinity is equal to 1. Okay, so this is, I think this is for the third one. Okay, yes, n over n plus 1. And this is for the fourth one. Okay, if you substitute n tends to infinity here, you will get infinity over infinity. And of course, you are already familiar with the L'Hopital rule. Then you apply L'Hopital rule, you differentiate the denominator as well as numerator. You will get 1 over 1 here. So the answer will be 1. Okay, so the limit n tends to plus infinity is equal to 1. So the sequence is converging to 1. Okay, the sequence is converging to 1. And then for the second one, you already checked with the calculator that this one is goes to 0. So the limit goes to 1. Okay. And then all the properties for the sequence also applies here. Okay. Okay, and then for the example 3, you can check whether the sequence converge or diverge. Okay, like this one, n divided by 2n plus 1. If you substitute n equal to infinity, then you will get what? You will get infinity over infinity. Then of course you apply L'Hopital rule. Okay, in this case somehow they divide with the highest order of the denominator. Okay, but by using chain rule, you can actually get the answer 1/2. Okay, 1/2. Sorry, not chain rule, L'Hopital rule. You use L'Hopital rule and get the answer 1/2. This one, this is 8 minus infinity. So the answer will be, I think, will be negative infinity. Yeah, it will be negative infinity. Okay, it diverges. If it is plus or minus infinity, then it diverges. If you, if the you get like a constant or a specific numbers, then it means that the sequence converge. Okay. Okay. I think you can do all of this at home. It's just that it's just something that you have learned before, especially during I think during the first chapter. Okay, when we discuss about limits. Okay. Okay, next one is monotone sequence. We have several definitions here. So the first one is strictly increasing. The second one is increasing. The third one is strictly decreasing. And the fourth one is decreasing. So there are two main things. One is increasing and another one is decreasing. And for each of the types that we have here, like one is increasing, but it's also divided into strictly increasing and the normal increasing. So what is the difference between strictly and just normal increasing? For the strictly means that it will never be equal to. So you don't have equality sign for the strictly increasing. But for the increasing, it is okay to have the equality sign. It's the same for the strictly decreasing. You don't have the equality sign for this one. But for the decreasing, you have the equality sign. Okay, so like this one. So this is strictly decreasing because this one and this one, they are not the same. 2 points are not the same. 2 terms in the sequence will never be the same. Okay, it's always increasing or bigger than the term before. Okay, and then for the second one, this is strictly decreasing. Okay, and then we have here the third one, 1 1 2 2 3 3. So like the first one is equal to the second one, the third one is equal to the fourth one. So it means that this is increasing and not strictly increasing. It is increasing, but it is not strictly, because for the increasing you can have the equality sign. Okay, you can have the equality sign for decreasing as well. For decreasing, you can also have the equality sign. For this one, for the third sequence, you have the equality sign. The first one is equal to the second one. The third one is equal to the fourth one. So this is equal. So it's just increasing, not strictly increasing. It's the same for the fourth one. 1 and 1, they are the same. 1/2 and 1/2, they are the same. Okay, so this is just decreasing and not strictly decreasing. Okay, but for the fifth one, 1 negative 1/2, and then you have 1/3, and then negative 1/4. Like you have alternate sign here. The first one is positive, the second one is negative, the third one is positive again. Okay, so it's like you cannot say that it is increasing. You cannot also say that it is decreasing. So it is neither increasing or nor decreasing. Okay, and then you can test for the monotonicity. Okay, so there are several tests. I think there are 2. One is to find the difference between successive terms. Okay, another one is by finding the ratio of the successive terms. So they are all summarized in this table here. Okay, if it is greater than, for the difference, then it will be strictly. If it is less, then it is strictly decreasing. If it is greater than or equal to, then it is increasing. If it is less than or equal to, then it is decreasing. Okay, so let's look at the first example. So the first example asks you for difference of successes, not ratio. Okay, so we have two tests. One is difference. Another one is ratio. So for the difference, it is the difference between two terms. Okay, so let's say you have an plus 1 and an. You take the difference. So this is the sequence that we have: 1/2, 2/3, 3/4, and so on. And the general term is given by this. Okay, so firstly, you know that the an is equal to this one, and then of course you can generate the an plus 1 term, which is n plus 1 divided by n plus 1 plus 1. Okay, or you simplify, you get n plus 1 over n plus 2, and then you take the difference. Okay, you take the difference. So this is an plus 1 and then minus an. Okay, once you take the difference, you simplify it and you get this. Okay, And of course, if you check it, is it possible that this is equal to 0 for n greater than 1? N is always greater than or equal to 1. It starts from 1. Okay, n start from 1. So n start from 1, 2, 3, 4, and so on. If n is equal to 1, it will be 1 plus 1 here, and this is 1 plus 2. So 2 multiplied with 3. So 1 over 6. 1 over 6 is greater than 0. This greater than 0. It will never equal to 0. So if you look at the table here, it should be what? It should be strictly increasing. But because it will never equal to 0. So it should be the first one. It should be strictly increasing. So it's strictly increasing. So this is by the difference. But of course, you can also use ratios of successive terms. Okay, so for the ratios, your an is equal to this one, n divided by n plus 1. Okay, just like before, because you still use the same sequence. Okay, an plus 1 is equal to n plus 1. Okay, n plus 1 divide by n plus 2, that's 1. Okay, and then you divide an plus 1 divided by an, and then you simplify, and you get this. Okay, n start from 1. What happen if you let n equal to 1? It will be 1 plus 2 plus 1. Okay, so the numerator will be 4 divided by 1 plus 2 divided by 3. So 4 divided by 3. So 4 divided by 3 is greater than 1. So it is greater than 1. Okay, it is always greater than 1. Is it possible for it to be equal to 1? It won't. It is not possible because for n equal to 1, you will have like 4 divided by 3. 4 divided by 3. What happens if you choose n equal to 2? It will be even larger than 1. Okay, but it won't be 1. Okay, so that's why it is strictly increasing based on this. Based on this, these properties, it is greater than 1 and not equal. If it is start with equality 1, then it will be increasing. Okay. Is it clear? Okay. Any question? No? Okay, good. So let's proceed. Okay, let's look at example 4. So for the example 4, we have sequence 10 to the power of n divided by n factorial. N start from 1 up to infinity. Okay. So your an is 10 to the power of n divided by n factorial. And an plus 1 is 10 to the power of n plus 1 divided by n plus 1 factorial. Okay. And then so this is by using ratio test. It's not mentioned here which test that we should use, but somehow in this solution they use ratio test. So an plus 1 divided by an, you simplify it, the solution, and you get 10 divided by n plus 1. Okay, what happens if you set n equal to 1? It will be 10 divided by 2. So 10 divided by 2, 10 divided by 2, is it? Ten divided by 2. But there's something that we have to look at here. It doesn't always depends on n equal to 1, which is the starting point. In this case, they want to show us that what is really matters for what in order to decide whether it is strictly decreasing or other cases is by choosing a big number of n. So let's look at this. So 10 divided by 2 when n is equal to 1. Okay, if you look at here, n is the whole thing here is greater than 1. Okay, but then if what happened if you have n greater than 10? Okay, so n, if you take n greater than 10, okay, so let's take n greater than or equal to 10. So let's take n equal to 10, then you will have 10 divided by 11. Okay, so for 10 divided by 11, it will be less than 1. Unlike when you take n equal to 1. If n equal to 1, then obviously this is greater than 1. Okay? So for n is for n equal to 1, then you will have 10 divided by 2, which is obviously greater than 1. But then this is not something that we want to look at. What happens if you have, let's say, n greater than 10? If you take n equal to 10, then this one will be 10 divided by 11. So this is less than 1. And this continues for larger n. For n greater than or equal to 10, these properties will hold. So this is something that we want to look at. Okay, so less than 1, if it is less than 1, means that from the table, it is what? It is strictly decreasing, right? So from the graph, from this properties here, it is strictly decreasing. And of course, by the graph, the graph will look something like this. So firstly, it is increasing, but after n equal to 4, it will be decreasing. Okay, and the sequence is said to be strictly decreasing because we observe when n tends to infinity, not for the first n, for the first 10n. Okay, not for the early n. We are looking for the n number of n, like n infinity or a very big n. Okay, so that is something that we want to look at. Okay, next one. Is it clear? Any questions? No? Okay, good. Okay, then we settle about a sequence, then we go to the series. Okay, so for the infinite series, it's just before we have like infinitely many sequence, it means that infinitely many terms. But what happens if we sum up? We sum up all the terms. So from the sequence, it will become series because of the summation. Okay, because of the summation. So the an infinite series is the summations of all the terms. Okay. Okay. Okay, and then we have definition here. The definition says that if the sequence converges to a limit S, then the series is said to converge. Okay, and S is called the sum of the series. Okay, if the sequence of the partial sums diverge, then the series is said to diverge. Okay, and the divergent series has no sum. Means that if you are asked to find the values for the summation, you cannot state the numbers because the summation diverge. You don't know the values for the summation. Okay, so let's look at the example 1. Determine whether the series 1, -1, +1, -1, +1, and so on converge or diverge. If it converge, find the sum. If it does not converge or if it diverge, then you don't have to find the sum because it does not exist. Okay, you don't have to find the sum. Okay, so the solution is S1 is equal to 1. Your S2 is equal to 1 minus 1. Okay, S3 is equal to S3. S3 is equal to 1 minus 1 plus 1. Okay, which is equal to 1. Okay, and then S4 is 1 minus 1 plus 1 minus 1 equal to 0. Okay, so the sequence of the partial sum will be 1, 0, 1, 0, and so on. Okay, and this is a divergent sequence, right? So this is a divergent sequence. Start from 1 and it goes back to 0, and then it goes to 1, goes back to 0, and so on. Okay, so it is not converging to a number. Okay, so this is a divergent sequence. Okay, it is a divergent sequence. Since it is a divergent sequence, then the series also diverge. So the series also diverge, and it has no sum. You cannot sum up. Okay, the summation does not give you an exact number. Okay, okay. Next, let's go to the first type of series, which is geometric series. Okay, so the geometric series is in terms of the summation. Start from 0 up to infinity. K start from 0 up to infinity. AR to the power of K. AR to the power of K. Okay. If K is equal to 0, then R to the power of 0 will give you 1. So the first term will be A when K is equal to 0, because the series start from 0. Okay, so the first term will be A. The second term will be AR. K is equal to 1, so it will be AR. The second term, third one will be AR to the power of 2, AR to the power of 3, and so on. Okay, and A is not equal to 0. If A is equal to 0, then everything will be 0. Okay, and this series is called geometric series, and R is called the ratio of the series. Okay, why it is called the ratio? Because if you take the ratio of the second and the first one, AR divided by A will give you R. If you calculate AR to the power of 2, you divide with AR, it will give you R, which is the values for the ratio. Okay, if you take AR to the power of 3, you divide with AR to the power of 2, it will also give you R. So that's why R is called the ratio for the series. Okay, so let's look at several examples here. 1, 2, 1 plus 2 plus 4 plus 8, and so on. Okay, so the general term is 2 to the power of K. Okay, and then the A will be 1. The first term is equal to 1, and the ratio is 2 divided by 1, which give you 2. 4 divided by 2, which give you also 2. And 8 divided by 4, it is also equal to 2. So if they are all the same, like R for each of the terms are the same, then it is confirmed that it is a geometric series. Okay, if somehow 2 divided by 1 is equal to 2, but for the third term, let's say the values is 6. 6 divided by 2 is equal to 3, which is not the same like the first one. The first one is 2 divided by 1, which gives you 2. But the second one is 6 divided by 2, which is 3. right? So they are not geometric series. For the geometric series, the ratio for each of the terms must be equal. Okay, in this case, it is equal to 2. Okay, so for this one, you have like 2 divided by 1, it is equal to 4 divided by 2, which is equal to 8 divided by 4. They are all equal to 2. So R is equal to 2. So it means that this is geometric series. Okay. And then like this one, the A is 1/2, negative 1/4. Negative 1/4, you divide with 1/2. What is the value? Is it the same with 1/8? You divide with negative 1/4. Okay, if they are the same, then this sequence, this series here is geometric series. Okay, and you can check with the third one, negative 1/16. You divide with 1/8. Okay, 1/8. They should give you the same values if they are geometric series. Okay, and then we have theorems here. It says that a geometric series is converged. Okay, will converge if R, the absolute value of R is less than 1, and it will diverge if the absolute value of R is greater than or equal to 1. If it diverges, then we cannot find the sum. If it converges, then the summation is given by this. The summation is given by A divided by 1 minus R. Okay. Okay, let's look at example 2. In each part, determine whether the series converge, and if so, find its sum. So 5 divided by 4k, 4 to the power of k. Okay. So for the solution in A, so you have k equal to 0. For k equal to 0, the A will be 5. 4 to the power of 0 will give you 1. So it means that your A will be 5. Okay. What about R? Your R will be 1/4, because this is actually can be written as summation k start from 0 up to infinity 5 1/4 to the power of k. Okay, 1/4 to the power of k. So your R here is equal to 1/4. So the absolute value of R is equal to 1/4, which is less than 1. So from the theorem before, the series converge. And the summation is given by this formula here, A divided by 1 minus R. So A is 5. Your R is 1/4. So you can substitute everything and get the answer. So this is the value for the summation. Okay. And then for this one, 3 to the power of 2k multiply with 5 to the power of 1 minus k. Okay, firstly you have to simplify. Okay, like this 3 to the power of 2k, it is 9 to the power of k. So it is 9 to the power of k, and then you divide with here 1 minus k means that it is 5. It is 1/5. It's 1/5 to the power of k minus 1. K minus 1. Okay. Then you have to combine. You have to combine this. How you gonna combine? Means that for 9 to the power of k, you can split off one is 9k minus 1, and then you multiply with 9. Okay, so this one will be what? Will be 9. You divide, you multiply with 9, divide by 5 to the power of k minus 1. Okay, so the a here is equal to 9, and your r will be 9 divided by 5. Your r will be 9 divided by 5, and 9 divided by 5 is greater than 1, so it is greater than 1, so the series diverge. Okay, so any questions? Is it clear? Okay, good, clear. Okay, example 3, find the rational number represented by the repeated decimal. So here you have 0.78784, okay. So what is the 784? It is repetition. One is 0.784 plus 0.000784 plus 0.000 up, and then you have 784 here. So it is repeated. Okay. Now we want to form the geometric series based on this this repeated decimal number. Okay. So A here is the first term, which is 0.78. For R, this one you divide with this one. This one you divide with this one. And R is also this one you divide with this one. So you get R equal to 0.001. Okay. So R is 0.001, which is less than 1. If it is less than 1, it means that it converges. You can find the summation by using this formula here. So A divided by 1 minus R. You substitute all the numbers and get the values. So this is the values, okay, for the summation. 784 divided by 999. Okay. So this is how you represent the repeated decimal places, decimal number 0.78478474 in terms of rational number, which is 784 divided by 999. Okay, I think you can also check with the calculator. Okay, and then I think you can do all this at home. Okay, they are all geometric series. Okay. Okay, now let's continue with the next topic, which is convergence test. So you may have lots of series, but how do you confirm that the series converge and diverge? You have many methods to confirm, or many tests to confirm that the series converge or diverge. So the first one is the divergence test. So what does this divergence test say? Okay, the divergence test says that if the limit of UK is not equal to 0, then the series UK, where the series of the summations, the series summation UK diverge. So UK here is the term for the series. Okay, so if the limit is not equal to 0, then it will diverge. So that's why it is called divergence test. If it is not equal to 0, then it diverge. If it is equal to 0, it may either converge or diverge. So you cannot make conclusion. You cannot make conclusion when the limit of UK is equal to 0. Okay, you only can make the conclusion when the limit of UK is not equal to 0. Okay, So let's look at the example. So you have this example, summation of k divided by k plus 1. Okay. So k divided by k plus 1, k tends to plus infinity. So this is the term for the summation. You take the limit, okay. So if you substitute infinity here, it will be infinity divided by infinity. It will give you infinity divided by infinity. So it means that you can apply L'Hopital rule, okay. So if you differentiate numerator, it will be 1. If you differentiate the denominator, it will be 1 as well. Okay. So the answer will be 1. 1 is not equal to 0. So from the theorem, it says that if it is not equal to 0, then the series diverge. Okay. So this series here diverge since the limit of the term, okay, UK here is not equal to 0. Okay. If it is equal to 0, then we have to go to another test to confirm that it is converged or diverged. We cannot say anything if it is equal to 0. Okay, but if it is not equal to 0, then we can strictly say that it is diverged. It diverged. Okay. The next one is integral test. Okay. So there's connection between this summation here and this integral. Okay. So this is 1 over k squared and this is 1 over x squared. K is start from 1. The limit start from 1. It goes up to infinity. The upper limit is equal to plus infinity. Okay. So the theorem says that if you have this summation here UK is converge if this integral equation converge. This summation diverge if this integral diverge. This integral converge if you have the values equal to a constant. If it diverge, it means that it is equal to plus infinity. Okay, either plus infinity or negative infinity. Okay, so let's look at example 4. We want to use integral test for this. Okay, so 1 over x integration 1 up to infinity. So since it is up to plus infinity, you have to take the limit. B tends to plus infinity and the upper limit is replaced by b. Okay, for 1 over x dx. Okay, and then you take limit b tends to infinity, and this one here, once you integrate, you get ln b minus ln 1. Ln 1 is equal to 0. So ln b, as b tends to infinity, will be ln infinity. It will give you plus infinity. So plus infinity means that this part here diverge. So it means that this summation also diverge. Okay, so the integral diverge, and so does the series. This one diverge, also this one. If this one converge, then this one also converge. Okay, and then you have P series. Okay, before that, this is when we use integral test. What happen if you use divergence test? For the divergence test, the UK here, is equal to 1 over k. The limit of uk, okay, k tends to infinity for 1 over k is equal to 1 over infinity. It gives you 0. Okay, so for 0, for the divergence test, if it is 0, then it is either it may either converge or diverge, so that there is no conclusion. Okay, so that's why you cannot do divergence test. Okay, divergence test cannot be applied here. Cannot be applied here. You have to use other tests like integral test. So for this case, integral test work for this series. Okay. This one also does not is not working for divergence test. If you take k tends to infinity for 1 over k squared, it will give you 0 as well. For the limit equal to 0, the test cannot be applied because there is no conclusion that we can make. It is either converge or diverge. Okay. But if it is equal to something else other than 0, so let's say equal to 1, then the series is confirmed to diverge. Okay. Okay, next one. I hope it is clear. If it is not clear, then please tell me. Please let me know. So far, so good. Okay, good. Any other comment or anyone want to share their views on this topic? No? Okay, so far so good. Then I will continue. Next series is called P series. Okay, so P series is 1 over k to the power of p. K start from 1 up to infinity. Okay, so for the P series, you have 1 over k squared, 1 over k to the power of 1/2. So this is for k to the power of 1/2. Okay, so this is for k to the power of 1/2. Okay, so the theorems for the P series, for p greater than 1, it converges. For p less than 1 and between 0 and 1, it diverges. Okay, so this is the theorems for the P series. Okay, so for this one here, so for this one, k is equal to, k to the power, k to the power of 1. So your P here is equal to, your P is equal to 1. Okay, it says that if P is equal to 1, that it will diverge. So this one diverge. This one, P greater than 2. Sorry, P is equal to 2, which is greater than 1. This one, converge. And then for the third one, k is 1/2. So this is not k, this is p. This is p. P is equal to 1/2. So for p equal to 1/2, it should be diverge. Diverge. So this is a P series. You can confirm with the integral test. Okay. So for this one, 1 over k, it says that the integral diverge, 1 over k. So for this one, 1 over k, it diverge because p is equal to 1. What about the second one? So for this one, it is also P series where p is equal to 2. Okay. If you look at the solution, it is equal to 1. The integration is equal to 1. It means that the integral converge. If the integral converge, means that the series also converge. Okay. So this is converged. The series converged. And if you look at the P series, for P equal to 2, for P equal to 2, for P greater than 1, they are all converged. So this one is converged. So it's tally. It's tally with that integral test. You can use either one of the tests as long as you can make the conclusion. Okay. So in the exam, you might face a question that does not mention the test. Okay, so you are free to choose any test that you want. Okay, and then for this one, so the general term is this one, 1 over k to the power of 1 over 3. So 1 over k to the power of 1 over 1 over 3. So your P is 1 over 3. So it should be between this 0 and 1. So it diverges. Okay, so this one diverges. Diverge. Okay, huh? Okay, and then you also have comparison, ratio, and roots test. So you have a lots of tests. You have learned about divergence test. You have learned about integral test. You have learned about P series, the test for the P series. Okay, now we go to the comparison test. I think let's take 5 minutes break before that. Let's have 5 minutes break. Okay. If you have any questions, let me know. Okay, let's continue with the comparison ratio and root test. Okay, so for the comparison test, you have like for the bigger series, that involve BK, if it converge, then the smaller series, the series with the term AK also converge. Okay, so this one is bigger than this one. Okay, so this, if this is converge, then this one will also converge. If the smaller series AK diverge, then the bigger series also diverge. Okay, so let's look at this. For example 1, okay, we want to use comparison test. So the test that we are asked to determine whether it converge or diverge is this one. So let's look at the first one, A. Okay, we want to compare with this one, this series. Why? Because we know that this series is P series. Okay, so this is P series. For P is equal to 1/2. For P is 1/2, we know that it is what? From before, P is equal to 1/2, it diverge. Okay, so the series diverge. So P diverge, this series here diverge. Okay, it is P series. Okay. We want to compare with this one. Okay. When K starts from 1 up to infinity. Okay. For K equal to 1, it will be 1/1. And this one will be 1 minus 1/2. Okay. 1 minus 1/2. So the denominator will be 1/2. So the answer will be 2. 2 is always greater than 1. Okay, so for K equal to 2, let's say K equal to 4. Okay, you can choose K equal to 4. You can choose any values for K, but I want to choose K equal to 4 because it's easy for me to take the square root. Okay, so for K equal to 4, it will give you what? 1/4 minus 1/2. So 8, 7/2. So 1/2/7. So 2/7, is it greater than this one? 1/4. Okay. Is it? Are you sure? Sorry. Let's check. 1/2. 1 over square root of 2. Square root of 4. Square root of 4 will be what? Will be 2. 1/2. And this part here, 1/2 minus 1/2. So it will be 4 divided by 2. 4 divided by 2, 3/2. Sorry. So this is 1/3 divided by 2, which is 2/3. So this is wrong. So this is 2/3. So 2/3, is it greater than 1/2? Yes. Okay, so this is correct and this is correct. You can check for difference value of K and to confirm that this sign is correct. Okay, and we know that this one is diverge. Okay, the small series diverge. Okay, the small series diverge. It means that the big series here will also diverge. Okay, but if the small series converge, we cannot say that the big series converge. We cannot say that. Okay, so this part here, this one called diverge, and it means that the big series here will also diverge from this theorems. If it diverge, if the If the small series diverge, then the big series, the bigger series also diverge. Okay. And then for B, you have 2k squared plus k. You want to compare with another series. So you can take 1 over k squared, 1 over 2k, 1 over 2 summation of 1 over k squared. Okay, so this is also P series with P equal to 2. So P equal to 2, P is greater than 1. Okay, so it converge. So P greater than 1. So it means that the series converge from the previous theorems. Okay. Okay, and then here, the original series 1 over 2k squared plus k and 1 over 2k squared. Okay, you can confirm that it is. You can decide whether it is less than or greater than by choosing any number. K equal to 1, you can test this. K equal to 1, K equal to 2, K equal to 3, and so on. Okay, and confirm that this inequality sign valid. So for this case, it is less than. Okay, so for this one, it converge. Okay, so if the small, sorry, so this one 1 over k greater than, we have proved that the series converge. So this is the series. Wait, please wait a minute. So this is a small series and big series. Big series converge. Big series converge. Okay, so we look at A. So the bigger series converge. So this is what we can confirm because it is P equal to 2. It is P series with P equal to 2. So it's confirmed that it converge. Then the smaller series will also converge. Okay. So the smaller series okay. So the smaller series here will also converge from theorem A. For theorem part A. Okay, part A. Okay. But of course, you have to confirm the inequality sign and make sure this one is less than this one. If it is greater than, then you cannot use that theorems. If this one is greater than, so your A, your this theorems here, your theorem A, your series A, if it is greater than theorems B, okay, so B here is converge. Okay, let's look at the theorems. Okay, so in that case, you have A greater than B, and this one converge. Okay, can you compare with these theorems here? So B converge, but B is smaller than A. Okay, B converge, but B is smaller than A. So if you try to rewrite it, it is B less than A and B converge. There is no properties like this in these theorems. B, which is the small series, it converge. then the series diverge. So this is diverge and diverge. For small series converge, there's no properties here, so you cannot check for this. Okay, so that's why you have to be careful with that. So before you can test by using comparison test, please make sure that this inequality sign is valid. Okay, you can test with k equal to 1, k equal to 2, and k equal to 3, and so on. For this one, if you test with k equal to 1, it will be 1 over 2 plus 1. Okay, 2 plus 1. And for this part here, it will be 1 over 2. 1 over 2. 1 over 3, is it less or greater than 1/2? Okay, should be less. 1 over 3 is always less than 1/2. What about k equal to 2? So if k equal to 2, then you will have what? 1 over 4, 8 plus 2. Is it less than or equal to 1 over 8? 1 over 10, is it less than or greater than 1 over 8? It is less than. So this is how you determine the sign. If it is correct, if it is less than, you can apply the theorem. If it is greater than, you have to be careful because it is not in the properties of the theorems. Okay, so you cannot use the comparison test. Okay, so I hope it is clear. Okay. Okay, so any questions? No? Okay, let's continue. And then we go to the comparison test. Okay, so for the comparison test, P is equal to the limit of AK divided by BK. P is finite. Okay. If P is finite and P is greater, this is not P, this is rho. Rho is equal to the limit of AK divided by BK. If rho is finite and rho is greater than 0, then series both converge or both diverge. Okay, so if we know that AK converge, then the BK will be confirmed to be converge. If AK we know that it is diverge, then the BK is confirmed to be diverge. Okay, so let's look at example 2 here. 1 over square root of k plus 1. Okay, we want to compare with 1 over square root of k. Okay, so 1 over square root of k is it is what? It is P series as well. P series with P equal to 1/2. Okay, so P is equal to 1/2. So P equal to 1/2 is what? It's diverge, right? Because P is in between 0 and 1. So this one diverge. P series. Okay, so this is P series. And then we want to find the limit for the ratio AK divided by BK. If we have rho is finite and rho greater than 0, then since we already know AK is diverge, it means that your BK is also diverge. Okay, so you check with the rho. Rho is the limit of this. Okay, and you simplify this. You can use L'Hopital rule for this one. Okay, and somehow you get 1 for the rho. Okay, rho is equal to a finite number because it is 1, and this rho here is greater than 0. Okay, rho is finite and positive. So of course, this B is diverge, so this one is also diverge. Okay, it's diverge as well. Okay. Okay, now for B. Okay, for B, the summation is 1 over is the summation of 1 over 2k squared plus k. Okay, and then we want to compare with 1 over 2k squared. Okay, so this is also P series. P series with P is equal to 2. So P equal to 2 is greater than 1. So it converge. Okay, so it converge. Okay, so this one here, you take the ratio from AK and BK. So AK you divide with BK, you take the limits, you simplify. I think this one also you can use L'Hopital rule and somehow you get equal to 1. 1 is finite, it is finite, and it is positive. Rho is greater than 0. Okay, it is finite and positive or greater than 0. Since this is converged, this BK is converged, means that the AK is also converged. So it is either both converge or both diverge. If this part here converge, then this one will converge. If this is diverge, then this one is also diverge. Okay. Okay, so I hope it is clear. So that is comparison test. So that is comparison test. And then we also have ratio test. Okay. For the ratio test, you have this rho is equal to the limit k tends to infinity for uk plus 1 divided by uk. Okay, uk plus 1 we divide with uk. If rho is less than 1, then the series converge. If rho is greater than 1 or rho is plus 1, then the series diverge. Okay, if rho is equal to 1, then there is no conclusion that can be made. Okay, that is ratio test. Okay, so for the ratio test, it's normally be applied to the series that have this what we call this. It is factorial. Okay, so this is factorial sign. It is normally applied to the series that involve this factorial sign. Okay, so this is called factorial. Okay, so if you have 5 factorial, it is also called 5 multiply with 4, multiply with 3, multiply with 2, multiply with 1. So this is called factorial. Okay, it's normally be applied to the one that involve factorial. Okay, so let's look at the first one, 1 over k factorial. Okay, 1 over k factorial. So for uk plus 1, it will be 1 over k plus 1 factorial. 1 over k plus 1 factorial. Okay, and then you divide with uk. uk is 1 over k factorial. So you simplify, you get k factorial divide by k plus 1 factorial. And then you simplify this. Okay, so since k factorial is equal to 1 multiply with 2, multiply with 3, multiply with 4, and so on up to k. But k plus 1 factorial is equal to 1 multiply with 2, multiply with 3, multiply with 4, and so on, multiply with k, and multiply with k plus 1. So if you take the ratio between k and k plus 1, it means that you are missing one terms here. It is 1 divided by k plus 1. So that's why you get 1 divided by k plus 1. And 1 divided by k plus 1, if you take the limit for k equal to infinity, it will be equal to 0. And this 0 is less than 1. It is less than 1. From this, if rho is less than 1, then the series converge. Okay, so since rho is less than 1, it means that the series converge. Okay, so the series converge because rho is equal to 0. Okay, for the next one, your rho is what? Your series is k divided by 2 to the power of k. Okay, K divided by 2 to the power of K. So this is your UK. So UK plus 1 is equal to K plus 1 divided by 2K plus 1. Okay? So K plus 1 divided by 2K plus 1. You multiply with this one here. 2K divided by K. Okay? And then you can cancel out whatever that can be cancelled out. So K plus 1 and K cannot be cancelled out. But 2K plus 1 is equal to 2K multiplied with 2. So what is left is 2. 2K can be cancelled out with this. Okay? 2K can be cancelled out with this. What is left is 1 over 2. Okay? K plus 1 divided by K is from here. Right? It's from here. This one. This part here. You take the limit K equal to infinity. It will be infinity divided by infinity. You use L'Hopital rule. You will get 1 divided by 1. Okay? So this one will give you 1. Multiply with 1/2, you get 1/2. 1/2 is less than 1. So rho is less than 1, then the series converge. Okay? So the series converge. So if it's from the ratio test. Okay, you can do all the other exercise or example at home. Okay, and let's look at the root test. For the root test, it is normally for the series that have this power, like to the power of K, and this one here, ln K plus 1 to the power of K. So this is actually equal to summation. What is this? K plus 1, K equal to 1 up to infinity. 1 divided by ln K plus 1, okay, to the power of K. Okay. So for this kind of series, you can use this root test. Okay. So the root test says that rho is equal to the limit of square root of UK cube. Sorry. So this is kth. How do you say this? Kth root. Okay. Kth root of UK of UK. Okay. Okay, so rho is this one. Okay. So this one UK is this to the power of K. If you take the kth root, it means that this K here to the power of K cancel out. Okay, so what is left is just the inner term, which is 4K minus 5 divided by 2K plus 1. Okay, and then rho is the limit of this. You substitute infinity here. It will give you infinity divided by infinity. You use L'Hopital rule. You get 4 divided by 2, which give you 2. 2 is greater than 1. So for greater than 1, for rho greater than 1, the series diverge. Okay, so the series diverge. So the series diverge because it is greater than 1. Okay. And then here for the second one, the rho is this one. The rho is the limit of this one. You substitute K equal to infinity, you will get ln infinity. So ln infinity, 1 over, if you sketch the graph for ln, K is equal to infinity. So ln will be something like this. So this is the graph for ln. So for ln infinity, the ln infinity will give you infinity. So 1 over infinity will be give you 0. Okay, it will be 0 because this part here will be infinity. 1 over infinity will give you 0. Okay, so 0 is less than 1. Okay, so 0 is less than 1, so the series converge. Okay, so the series converge. Okay, so that is how you use all the tests. Okay, I think there is a table here that summarizes all the tests. Yeah, this one. I think this is the table that you need to at least print out um, and at least I think you should have this and know all this. Okay, these are all the tests that might be useful for you. Okay, please print this out. Okay, I think that's it. The next topic is already McLaurin. McLaurin is not in our syllabus. Okay, so we finish our syllabus. Okay, congratulations to all of you because you already finished the syllabus. What is waiting for you now is the final assessment. Okay. So thank you to be with me for these 13 weeks. Okay. We face a lot of difficulty during online class, but I hope we survive. Okay. I hope we survive. If you have any questions, please let me know. But I hope this chapter is clear. You have to do a lot of exercises because it involves a lot of tests. Okay. If you don't do a lot of exercises, you might get confused. Okay, you might get confused either to use either test A or test B or test C. But if you are familiar with the types of the exercise, okay, or types of the series, I'm sure you will know which test that you should apply. Okay, your final assessment will be from week 13. Sorry, 15. Week 15. Okay. I'm not sure the exact date yet. Okay, but it won't be more than 12 hours. It won't be more than 12 hours. I think I just said it to be like 3 hours. Okay, if any of you have like internet connection problem, please let me know. Okay, all the answer script will be submitted through the My Guru. Okay, My Guru. Okay, so make sure you compile your answer script so that it's only one PDF file. Okay, you make sure compile it so that it's only a single PDF file, so that it's easy for me to check. Okay, so please make sure that you do it. And then another thing that you have to be careful is, please make sure that your file is set to be public. Okay, not private. Okay, because some of you, even after I request to view, you still do not respond to it. Okay, it takes like ages for me to receive the reply from you. So make sure before you submit, you check it that the setting is public. Okay, so I don't have to request in order for me to view. Okay, Okay, I think that's it. If you have any questions, it's a Q&A session now. Okay, you can ask me any questions. Your final assessment, the topic will be integrations, all related to integrations. Okay, because for the differentiation we already discuss it in, I mean, it's already asked in tests as well as quizzes, right? So for integral, it is left for final assessment. Okay, anything? Anyone want to ask questions? No? If no, then that's it. Thank you very much. I think that's it. I don't have anything to say. Okay, so thank you very much. I will stop the recording now.